Well, looks like we can start. Welcome back, folks. We're nearly done with week 13, so that means the semester is just about over. As far as the exams are going from Monday, I'm a bit behind on the grading. I may not get them graded in time for Thursday. Sorry about that. But I should have grades posted onto Moodle probably Friday, pretty soon, I'd say. And then exams will be passed back next Monday on the 18th. For the other announcements, we're halfway through chapter 14. I posted an extra example down here because I felt like we ought to do at least 2 examples since one of them was done right before the exam. It's easy for that material to get kind of foggy after that turnaround time. So we'll have a couple examples to get through in chapter 14. After that, let's see where we're at. We're moving into chapter 15 on hypothesis testing. This one is a pretty big chapter, and it could potentially be the last chapter of the semester. So we'll take our time with it, consider those topics very carefully. Essentially, what hypothesis testing is a different way to do inferential statistics. It won't be confidence intervals. We'll ask direct questions about the parameters that we were dealing with. Then looking forward in the schedule, this is a tough week, but we'll get through it. This week is hard because it's the week right before Thanksgiving break. I'll be there all the days, so we'll get through it together. After that, we'll come back on this week. This is our next to our last week here. We'll be finishing off topics on, let's see, that's December 2nd. Wow. We'll be finishing off topics on the 2nd. 4th, I want to be pretty much wrapping things up, and we'll be transitioning over to just reviewing for the final exam at that point. So that's where we're at so far, folks. Congratulations on getting through it so far. I do have a bunch of extra credit opportunities that I do want to post here, so those are going to be coming over after the weekend. But any questions at the moment? Let me scroll to the right spot here. There we go. So we have quiz number 9 due tomorrow. That one's based off a confidence interval in chapter 13, which was the last problem on the 3rd exam, pretty much. Then quiz 10, it's going to feel almost the same. It's just a new confidence interval, but the confidence interval will be a one dealing with the mean. So the kind of problems we're about to launch into. Any questions, comments, or anything else so far, folks, before we get started? Okay, let's jump in. So chapter 14, it's a kind of odd chapter when you read through this section because it takes a lot of time to describe what are the central limit theorem properties trying to say and everything along those lines. And also there's a whole new distribution, inverse T calculator. But after you get through all those parts, it's pretty much just this. Instead of using the old confidence interval where we had p hat, we put in y bar. That's just the new statistic along with this problem. Instead of a t star, we had plus or minus z star. Instead of standard error of x bar, we put in standard error p hat. I'll delete this in a moment, but this is just to say our methods are really actually pretty nice in a way, that there's a lot of parallelism there between chapter 13 and chapter 14. Things that are new are calculating t star. We'll review that in our next problem. And the fact that we have to deal with degrees of freedom to get an accurate value for t star. So the way this all comes together is looking at a specific problem. We define a parameter, calculate the standard error, that's just the standard deviation, divide by square root of the sample size. After we do that, we come up with our critical number t star, and then it gets put right back together in this kind of way, like we did in this problem. The moment we calculate the upper and lower bound, that's our full confidence interval. And in the interpretation, it almost feels redundant in a certain way because it always goes the same. It just depends very crucially on what you said mu was on the very first step. Well, let's take a look at a fresh problem. This one's a little bit more of a challenging problem because when you look through this, suddenly we have the raw data. And our goal now is we have to extract the summary statistics relative to that data. And this is kind of a fun problem in a certain sense. We looked at this, I think, around the start of the semester. Let's review what the context is that tell us dementia is the loss of intellectual social abilities severe enough to interfere with judgment, behavior, daily functioning. And they tell us Alzheimer's is the most common form of dementia. That in this particular article, living with early onset dementia, the authors explored experiences and struggles of people diagnosed with dementia and their families. But they go on to say right here, we have a simple random sample of 21 people. So that's good information for us. We might as well record. Sample size is 21. They all have early onset of dementia, and they gave the following data on age of diagnosis in years. So that's what the data here refers to. The moment it says that, if this was, say, a real exam problem, it might not be a bad idea just to say here, age at diagnosis, just as a reminder that that's what the context is referring to. Wouldn't be a bad idea to underline something like this: the following data on age of diagnosis. Okay, so that's our problem so far. Well, we still need X bar, or excuse me, not X bar, I forget what semester this is, Y bar, our sample mean, and S, our sample standard deviation. You can get those two, we can move through the rest of the methods pretty quickly. So that means back to the calculator. It is tedious to have to do this in the middle of a problem, but this is something that can happen on the final exam, for example, where we do have that extra time to crank out the data. So first button to hit is stat. Hit enter on the edit field. I'm going to clear out just everything because we're not doing regression. Let's just hit clear on this and enter. With L1 selected, hit clear, enter again. Now we've got a blank slate. And I'll get quiet for a few moments. Let's enter in that data. Okay, I think I've got all the data put in. Let's just take a couple more moments. Okay, anyone need any additional time? Oh, just a couple people, no worries. This is actually a lot of data. We usually have a smaller data set for these kinds of problems. How about folks on Zoom? Are we ready to go? Okay, sounds like we're all set. So if you know how the next steps go, you probably already have the values. But just for the sake of review, next thing you do is immediately hit stat button, move over to calculate, and just hit enter right here. We want option one variable statistics. L1 should be there. And if that's the case, everything should be all set up. Frequency list should always be blank. So if there's something there, just delete it. And there's our information. We have X bar, top of the list, or excuse me, Y bar on the top of the list. That's confusing when the calculator even agrees with that for me, that notation. 52.52. Let's say, it didn't say anything to round to. So I'd say do what makes the most sense. 2 decimal places should be sufficient for this problem. Then for S, recall we have to be pretty careful with that one. It's SX we want for the standard deviation. It's 6.47. Not a bad idea to include units on these, especially since it's quantitative data. There will be a unit. This is years on this one, and years on this one. So on average, the age at diagnosis for early onset dementia is 52.5 years, 52.52 years, and standard deviation of 6.47 years. It's kind of scary in a certain sense, but now we're ready to launch into the problem. We want to describe the unknown parameter, and that means for these data, since it's quantitative, we start by writing out mu. That's a decent thought to connect right here. We have quantitative data. And so that tells us the parameter is mu in this problem. Mu is the mean, but we could also call it average if you prefer. It's totally up to you. I'll write down here, mu equals the true mean, and this is where it gets tricky. We have to say the mean of something specifically. Anyone see what should go here? Well, not quite. Well, this one's going to be a mean, not a standard deviation. And also because it's a parameter, it doesn't have a value. We're just trying to describe what is it actually in the context of this particular problem. But here's how the format of this would always go. Let's write down just a little structure here to help out. If the parameter is mu, then in any one of these problems, you would write out this. Mu equals the true mean, or you could say the population mean, or you could say the population average or the true average. All those are stylistic choices. But we have to say mean or average somewhere. There's going to be the true mean of, you put in here the type of data. Let me see. Let me see if I can convey that in a better way. The true mean of, let's put here, whatever the data well, it wouldn't be any value in the calculator because mu is truly an unknown. We can't actually put a number on it. All we're trying to do is describe what it would actually represent verbally. But for the structure of it, we'll say it's the true mean of whatever the data is actually representing would go here in the first blank for all. Then here we have to say mention the population. And it's a tricky enough problem that, you know what, before we fill this out, let's see what we did just in the past, just to get some extra help on this one. So if we go to chapter 13 just for a moment, 13.3 will do the job. Let me widen that out. Let's find out where we put in a parameter of something. There we go. It was in this problem. When we were dealing with, let's put this on kind of a side-by-side display. When we're dealing with this problem with the categorical data, we wrote P. Now it's a true proportion of something. We had to say that part right there, true proportion or population proportion. Instead of proportion, you could have said percentage. But then we had to say what the population was. That's what we're mentioning down right here. We have to mention the population at some point. And we also had to say what a success was in the particular problem. And this one, a success was surviving for 5 years after treatment. In our problem down here, when we're saying the true mean of something, that's kind of like saying what the success is. We just have to mention what is the data of actually? What are we taking the mean of really? Anyone see what should go here so far? Yeah. Exactly. It's going to be true mean age at diagnosis for all people with early onset dementia. And that's all we have to say. It's kind of uncomfortable in a certain sense because, again, we don't know what mu is, but that's why we're doing a confidence interval. The whole point of the confidence interval is to now estimate mu. And we do have an estimate. It's right here, 52.52 years, but that estimate doesn't reflect any sense of error. And so that's why we're also going to do a confidence interval at the same time. But looking at our answers so far, when we said the true mean age at diagnosis, here's where we were saying what the data represents. And then when you mentioned people with early onset dementia, because we said all here, just for the extra emphasis, this is certainly describing the population. So we are concerned with everybody who's afflicted with this condition. On hand, we have just 21 people. It was a random sample, so that's very helpful information. But these 21 people, since it's a simple random sample, could very well actually represent well all people with this condition. So now we're ready to start cranking out a confidence interval to give a very good honest estimate of that value there, mu. Any questions at the moment? Okay, here's where we're going to start to need our summary statistics. So let's take this along with us. I think that's a good spot to scroll down to so far. When it says calculate the value of the standard error, that's tricky because we have multiple standard errors so far. What we did in the past was that formula, but that's purely for categorical data. The moment the data becomes quantitative, the formulas change, including the standard error. It goes to this now. SE. The statistic is X bar. Oh, sorry, did that again. The statistic is Y bar. Control Z to the rescue on that. Sorry for folks working in pen. Control Z doesn't work that well. Formula is S divide by the square root of your sample size N. Kind of a nice computation again, because looking in the past, that one was a tricky computation, but here, much more simplified. When it says S, we're referring to the standard deviation, 6.47. The N in the formula is referring to the sample size, which is the 21 individuals. And then we just jam it all into the calculator. So this is the fun step. Go 6.47, divide by, hit second key and power 2 to get that square root of 21. Should look about like this in your calculator. And the value I've got to 4 decimal places would round up to 1.4119. Does that look right to folks so far, that value? Awesome. So always nice to have a better formula for standard error. Well, I shouldn't say better, but simplified formula. So 1.4119. Next thing we would want for a confidence interval is the critical number T star. We mentioned what the steps were, where you don't actually have to draw a diagram each and every time. So let's just reduplicate them here. Again, it was a long time since we did our last confidence interval. It's always unfortunate to break these in half across an exam. So the review on this is for step 1. That doesn't look like a step. In step 1, we want to calculate this. This is the area that's going to go into the calculator. It'll be equal to 1 minus whatever your confidence was as a decimal number. And then we divide it by 2. This automatically then gives us our T star. But before, oh, hang on. It doesn't automatically give us our T star. Before we get our T star, we want one extra formula. It goes, let's use this color as well. DF stands for degrees of freedom. The formula for this is sample size N reduced by 1. So our sample size, we can look it up right here. N goes over to 21. Minus 1 tells us the degrees of freedom in this problem is 20. So that's enough to put this all into the calculator and get a value out. So it's tricky though, because even the TID3 calculator can't do this step. So we'll do it a second way just to show for the help on homework. what you would do if you have a TID3 calculator or something else as well. So first step, hit second, vars, and we need inverse norm. Might as well put that on the notes. So step one, do the area. Step two, calculate the degrees of freedom. And then finally, step three, use INV. Sorry, I said norm. It's actually inverse T. Misspoke and mishighlighted that thing. Inverse norm would be nice, but that would be in chapter 13. We're working on the T distribution for this one. So use inverse T. And you know we're picked the wrong one because inverse norm doesn't talk about degrees of freedom whatsoever. If you go to inverse T, that's where things line up here. So I'll just type that in directly and verbatim. 1 minus 0.99 divide by 2. Now, when you go back to this spot in the calculator, all you have to do if you go to a different problem, go over here and just overwrite. So for example, if your next problem on homework is a 95% confidence interval, you could just change it like that pretty rapidly. But make sure, always change the degrees of freedom because it's practically a guarantee that's going to be different in every single problem you do in this course. So our degrees of freedom is size 20. Hit enter a bunch of times and we get our values out. So our value is 2.8453. We always grab the positive value. Although, again, for the purposes of quizzes in this class or exams, I wouldn't mind if you grab the negative value. Web assign, or excuse me, my stats lab might though. So we always state the positive one. Well, we've got our critical number down. And again, just to show what to do if you don't have the TID4 plus, here's what the next step would be. Just to also reiterate, on a real exam setting, I would put down here, use the fact that the critical number is 2.8453. So if you don't have a TID4, don't fret, you don't have to buy one for the purposes of the final exam. Your calculator's been good so far, and it'll still be good on the final. But for the homework and quizzes, we have to do it ourselves. So let's go and grab this right here, inverse T calculator. Sorry for the ads. This website seems to have been hijacked with a lot of them. What we need to put in is our degrees of freedom. So overwrite this with 20. We need a confidence, up and down changes that. We need a confidence level up to 99%. And then try to skip through the ads, click calculate. Ignore that one. You go down to that one right there, 2.8453. Well, by the way, that's the value we should have in our calculators or in our document so far. Any questions whatsoever, folks, getting that critical number? Minimize those ads for a moment. There we go. Yeah, go ahead. Oh, it's for the calculator area. It should look like this. 1 minus 0.99 divided by 2. And so just to visualize it back in there, go down to inverse T, and it should look like this altogether. I think the only mistake that would be kind of easy to miss is forgetting that parenthesis right there could change it quite a lot. Other questions so far? Okay. Well, now that we have pretty much everything we need, we have the standard error, T star, we have our summary statistics down below. All we need to do now is just state the confidence interval and calculate it. So here's where we're going to go. Y bar, add or subtract, T star, which is multiplied by standard error of Y bar. So that gets us started. Then next step, I think the mathematical statement for what we're doing is the method's called plug and chug. So we're plugging in for Y bar 52.52. You see on the bottom of the page there that we calculated ourselves. So that's awesome. Add and subtract T star from the last step, 2.8453. Then multiply that thing by the standard error. That one is in two prior steps, 1.4119. We're going for two places when we go to round our final answer, but we'll keep the extra precision that we have before we get to that rounding. I think at this stage, we're done with the summary statistics. And this is just the kind of relaxing phase. We go back to the calculator, put in the first value with a minus, 52.52 minus 2. Oh, I forgot my minus key. Let me try again. Minus 2.8453. Multiply it. I'll use parentheses to indicate multiplication. 1.4119. Okay, so this should be my lower bound since I used minus. To two decimal places, that's 48.50. Anyone recall what the unit was, though? Was it inches, feet, second, years, decades? Years, good call. It's a good idea to put it right here. You wouldn't be docked if you didn't, but it helps us with what we're going to do in part E because we're thinking about the context by putting in that unit. So it's from 48.50 years. That's less than mu, the unknown parameter we specified in part A, which is also less than, now go back to the calculator, up arrow, hit enter on that to paste it down. And we're going over to that position. Overwrite with addition, enter gets you to your next upper value. So I got 56.54 years on that one. Is that looking all right to folks so far? Okay, well, we've got our confidence interval. And the biggest challenge in statistics is not actually calculating the confidence interval. It's just conveying what it's trying to say. One thing we mentioned before, we can never really say to people is we have 99% confidence, 48.50 less mu, less 56.54. No one has a clue what you're talking about, and you sound like a robot at that point. So we have to break this down, say exactly what we mean, referring back to the context. But referring back to the context just simply means this time that we go up. Presumably you could see this all on one page, but for me, I just have to scroll up, come back down here, and just reconvey what this is all saying with that description of mu. Even if it's wrong, you won't lose points a second time on a real quiz or exam problem. So we begin by saying, with 99% confidence, the true, I'll go with average. The true average age at diagnosis for all people with early onset of dementia is between those two values. So 48.50 years and 56.5054 years. Sorry, talking's hard today for some reason. Well, we got it, folks. That's the conclusion to the confidence interval. One thing to be careful with, though, is if you're looking at this from 48.50 and 56.54 years, and you think, oh no, well, I know a Fred that's in that age range, don't fret, because remember, this is about mu. It's the average of everybody. It's not talking about one specific person whatsoever. So some people with early onset of dementia had age 41, for example. I'm more older than that, but that's just one person in particular. The average of the whole data set was 52.52 years. So don't forget, this is always talking about overall average, never about one single individual in particular. But we did, folks. That's the conclusion of that confidence interval. I felt like It's been a while since we did this kind of confidence interval. We have a bonus problem as well on the Moodle website we'll take a look at next. But any questions or comments at all, folks, getting through this one? Okay, if this all makes sense, then congratulations, you're getting through statistics. Hypothesis testing, it's a little bit tricky, but it's really not too much more than this once we break down the concepts and see how the full procedure ends up going. Let's get this all saved up, and we'll take a look at our next problem. So the bonus problem was put into the Moodle website here. Oh, I can't open that one. Sorry, just figuring out where my windows are. There we go. It's right here under the main one. I also posted under the Blake lecture notes as well, if you prefer the Word document. And oh dear, I don't think I put it on my thumb drive, so I actually do think I need to go grab that. Thought I had everything before starting class today. So I want this one. I guess it's a good reason that I do put these on here. Didn't expect to have to use it myself. Oh dear, that's gonna be a problem. Maybe figure out where it downloaded to. Sorry, technical issues. I guess you could call this part of class so far. Okay, I need to grab that, throw it here, then tell Microsoft Word not to worry about viruses. Oh, it doesn't care anymore. Okay. So here's our next problem we'll take a look at. I felt like for today, we already did a problem where we had to crank out the summary statistics, so I just posted them here, but looks like I made another misrecollection. Instead of X bar, let me just fix that and put in Y bar once again. I appreciate everyone's patience with those random typos. Okay, so brand new problem, let's take a look at this context. We're told calcium is the most abundant mineral in the human body and has several important functions. Most body calcium is stored in the bones and teeth where it functions to support their structure. So we get a biology lesson. Here's where the statistics problem starts. Recommendations for calcium are provided by dietary reference intakes developed by the Institute of Medicine of the National Academy of Sciences, so sounds serious. Recommended adequate intake of calcium for adults ages 19 to 50 is 1,000 milligrams per day. So that's their recommendation for everybody in that age range. Here's where the problem gets interesting. Let's put in a little page break. A simple random sample of 18 adults with incomes below the poverty level gave the following daily income calcium intakes. So now it gets interesting. Based on this guideline, we can presumably assume adults know they need that level of calcium, but things are harder when you're below the poverty line by a lot, and so anything can happen. We have a simple random sample of n equals 18 adults in that situation. Some of them are at calcium levels 774 per day, which is well below guidelines. Others are doing just fine, 1192, for example. But we want to see how they're doing on average now. The average is below 1,000. But the astute observer would realize that doesn't really tell us much. Sure, it's below 1,000 milligrams per day, but it's just an average. There could be error in finding that average. And so we need to do a full confidence interval procedure to see if we really should be worried by these data and that average. Notice the standard deviation is also pretty large as well, and that plays a huge role in this kind of problem. So to get started, as all of these problems go for confidence intervals and hypothesis testing, we begin by just saying, what is the parameter? Observing that the data is quantitative, all the numerical values we have, we'll write out mu equals. Let's actually put this one thing we put on the last problem. It's always good when you're looking at data to think, what does this data represent? And this is daily calcium intake in milligrams. So mu is going to be equal to the true mean, or you could say average, calcium intake you don't necessarily have to mention that the unit is milligrams until we get to the confidence interval. But we do have to say one additional thing. We have to mention the population next. So we'll say mu is the true mean calcium intake for all, and then something has to go here. Any volunteers for mentioning what the for all is going to be? Yeah, absolutely. So for all adults, ages 19 to 50, and there's even a little bit more here. Anyone spot the last remaining bit to specify the population? Absolutely. That seems to be a big feature of this problem as well. So let's mention it down here. Good call, folks. We've nailed that parameter down. So true mean calcium intake for all adults aged 19 to 50 below the poverty line. Okay, so that's the specific population we're dealing with. That last part was definitely a good call, since it seems like that was, let's see, a big part of the problem right here. Definitely highlight worthy. So once we have mu nailed down, it's just a total repeat of what we did on the prior problem. We have a sample mean here. We have a sample standard deviation here. And next, we want standard error. This one says standard error of the sample mean. So that's really helpful because now we can write SE, Y bar. Literally, this says S for standard, E for error. Parentheses are just saying of, literally. And Y bar is the sample mean. There's just a faster way to say it all symbolically. As before, it's S divided by the square root of sample size n. So that means in our problem, it's 172.0 divided by square root of 18. And all that gets jammed into the calculator on the next step. So let's go 172 divided by the square root symbol. Square root of 18 is not a very friendly number, but that's okay. Calculator doesn't care. And we have a standard error to 4 decimal places of 40.5408, rounding up. Is that looking okay to folks so far? Okay, standard error done. On to the next step then. We need a critical number T star. So let's go through those same steps. Step 1, we find what the area ought to be. The area in this problem looks like it's a 99% confidence interval again. Sorry, that's a little bit redundant. We can change that if we'd like, though. This is our problem. Any volunteers to change it if we'd like, or should we just stick with it? Your choice. Let's go 95, good call. Makes it feel like a slightly different problem, right? So with a quick check, let's go with a 95% confidence interval. I'll put that in red just to convey we did change that one after the fact. So let's go 1 minus the 0.95 divide by 2. Yellow highlighting helps out here. Step 2, we calculate degrees of freedom next. So degrees of freedom by formula is always sample size n minus 1. Which means if you never write down this formula, you'd never hurt my feelings. It's okay to just say it's got to be 17 in this problem. But just for the sake of learning it, it doesn't hurt to write it down. So sample size was 18. We're subtracting 1 from it. That tells us 17 degrees of freedom in this problem. Then step 2. Excuse me, that was step 2. Step 3 now. We use inverse T to get, well, let me say here, or the calculator, on the website. On Moodle is a better way to say that, to get our T-star. So with those steps, we're pretty much where we need to be. If you're using this calculator here, at second vars, punch 4 for option 4, inverse T, and it reset on me. I'll go 1 minus 0.95 divided by 2 on the first line. Second line, put in 17 degrees of freedom, and that should do it for us. So in my calculator, let me know if you're getting something different. I'm producing a critical number 2.1098. Kind of going through these a little bit fast. I mean, now we're about ready to calculate the confidence interval, but any questions at all, folks, getting to that step? Okay, it gets a bit methodical after you've done a dozen of these, and we've practically done a dozen of them if you include chapter 13. But we should still be careful when it says the confidence interval for the unknown parameter. You have to know what type of confidence interval. Because we said mu up here, it's going to be y bar.
Is that also change to 95?
Oh, it would. Thanks for catching that. That's one thing that's kind of sucks about it. Edit is lots of things could have to edit right after it. Good eye. That's sometimes how I make typos on exams by mistake, making one change, thinking it's a good one, but forgetting to track it all the way down. So we've got y bar, we're going to add and subtract. The critical number T star, which gets multiplied by standard error. SE of y bar. So to make this all happen, I think we got to scroll up here for just a moment and see our statistics. So 947.4 in place of the sample mean y bar. From that, add and subtract critical number T star. So this figure, 2.1098. And then last thing to substitute in, for standard error y bar, go to our step part B there, and it's a 40.5408. So that's our total confidence interval. And again, if you're doing this as a, say, quiz problem or a problem on the final exam, putting this down on paper is massive partial credit. So that way, anything that goes wrong with your calculator isn't going to be such a big deal, really. But we still have to calculate it, so let's put in 947.4, starting with a minus for the lower bound, 2.1098, and multiply that by 40.5408. So my lower bound on this one, and this is in milligrams for calcium intake, would be 861.88. Milligrams, so that figure is less than mu, which is less than, go back to the calculator and do the same kind of thing. This calculator often up arrow, but this also works in the T83. Hit this, oh, good call, so 0.87 there. I'm not too sure how it got to that extra 8. Thanks for catching that. That rounds up to 0.87 in that position. Thanks for spotting that. I'm always kind of amazed at the weird typos I make when I write these things down. But next, in a T83, hit the second key, then opposite corner, the enter button, and that'll carry down your last computation. And we already can guess the change. Just go here, overwrite with plus. Now we've got 1,032.93. In milligrams. And this is milligrams of daily calcium intake. Not super important to write that in, but if the unit helps with the context, saying just a little bit more also helps as well. Any questions at all, folks, coming up with that full interval? Okay, so last step. We need to carry down what the actual parameter was. I'll just take that as a screenshot. As a better screenshot. Note that there's a part F on this one. We'll get to that later. Let's just hide it for the moment. We want a practical interpretation of the interval we just calculated. Excuse me. So we can begin by saying something along the lines of, we are 95% confident that, I'll just say here verbatim what we said before, the true mean calcium intake for all adults 19 to 50 years old, I guess that's not verbatim, but let's keep going, below the poverty line is between 861.87 milligrams and 1,032.93 milligrams. So that's our end conclusion on that one. Any questions or comments, folks? Getting to that last step there? Yeah. Yeah, absolutely. That'd be a great way to say it. I'd say the only way we could ever really lose any kind of credit on this sort of statement here is the following way. We shouldn't say 90.95 probability. And there's a couple reasons for that. We're trying to give a interpretation that will make sense to people without having ever taken probability courses or statistics courses in the first place. Probabilities are abstract, but there's another bigger reason. When we say 95% confidence, we're not saying there's a probability of 0.95 that mu is between those two numbers. Every time we do a simple random sample, those two numbers on the left and the right are always different because every new random sample gives you a different sample mean right here. So when we say 95% confidence, this is what we're really meaning. We shouldn't say 0.95 probability. We say 95% confidence because there is a 95% chance this method produces an interval really containing mu. And this is a pretty complicated statement in a certain sense. So again, there is not probability 0.95 that mu is between those two numbers. We would have no way of assessing that, but there is a 95% probability that the entire confidence interval method, this one, will contain the actual parameter mu inside the interval. So we're saying our method has a 95% success rate is essentially all we're saying, but whether mu is actually inside there, we don't know the probability of that whatsoever. Well, any questions or comments, folks, so far? Okay, well, there's a follow-up question to this one. This follow-up question is naturally leading into what we're trying to do in hypothesis testing as well. It's kind of a surprising question at the same time, our answer to it, in other words. It says, does this study provide significant statistical evidence that adults with incomes below the poverty line have calcium intake levels below 1,000 milligrams per day on average? Let's think about that question. Would you say yay or nay to that? Or how do we even think about it is another way to think about, is another way question to ask. While we're thinking about that, notice we do have an interval here that's in inequality form, but we could take this whole interval and write it down on a number line. It's still an interval. This is what it would look like. We have a number line starting at, well, we have a point starting at 861.87. We have another point over here, 1032.93. And now the question is, where is mu? That's a weird question, but one thing you could actually put here is y bar is always in the direct center of your confidence interval every time you calculate it, no matter what the chapter is. P hat would be in the middle in chapter 13. The statistic y bar is in the middle in chapter 14. But back to the question of where is mu? We want it to be in the middle of this interval, right? Presumably as close to y bar as possible, but it can literally be anywhere. Mu could be here, outside of the interval. That would mean our sample was really weird, but that can happen on random sampling. Sometimes when you sample things randomly, you, by random, get a biased sample. It could happen. But mu could also be way out here. That's inconvenient in a certain sense. What we're trying to say is we don't really know where mu is at all. But don't forget, we do have a 95% confidence interval. And this interval, 95% of the time, places mu somewhere inside here. Let's take that off so we can emphasize mu better. I'll put mu just randomly. Doesn't have to be in the center. It could be really close to the upper end, really close to the lower end. But let's say we are 95% confident mu is here. Inside the interval, in other words. But what else is in the interval? We also have that figure right there, 1,000 milligrams.
So
Maybe it could be above it too, right? It could be anywhere inside this interval, but this is the critical thought so far. 1,000 milligrams is also in that interval. So if our interval succeeded, then it's going to be in here somewhere, and there's a 95% probability it succeeds. There is a chance that this mu is here, equal to 1,000 milligrams, or it's even here above 1,000 milligrams. We don't know until someone takes a census and actually calculates it, or gets a bigger random sample with a narrower confidence interval. That would help out quite a lot. But we're stuck with the study we have, so we have to work on it. So with the bigger picture here, would you say we have evidence mu is below 1,000 milligrams, or we don't have evidence?
95% confidence for the most part.
It's kind of tough because remember, mu could be here, and that messes everything up, right? It muddies the picture tremendously.
Oh,
That's the trouble, exactly. What made it a no is the fact 1,000 is in the confidence interval. It means it's plausible that mu equals 1,000 or is bigger than it. It could happen. So we lack that significant statistical evidence that we were asking about. Let's write this all up carefully though, because it's a pretty tricky question. And like we mentioned, this is part of the logic of what's going on in hypothesis testing coming up. We'll say here, since 1,000 milligrams is inside our confidence interval, it is plausible that mu could be potentially greater than or equal to 1,000. I mean, it's also plausible that it could be less than 1,000, but we are not certain that mu is always below 1,000. If our 1,000 value was somewhere here, ignore that number, that makes it incorrect, we would have said, yes, we have excellent evidence that people below the poverty line have below 1,000 milligrams in their absorption per day. But because 1,000's here, we say no. This means we do not have significant statistical evidence that mu is less than that 1,000 being referred to. And I think this write-up is still kind of tricky because when they said adults with income levels below the poverty line, on average, they were referring to mu here as well. So, in other words, if 1,000 is inside your interval, this type of picture would always lead to an assessment of no. Well, any last questions or comments, folks, so far? Okay, let's save this up. I'll get both of these documents uploaded. And our next adventure is going to be actual hypothesis testing. Like I mentioned, hypothesis testing is tricky, but it's a different way to view what we're doing here. It's still inferential statistics, conclusions on confidence intervals, and two-side hypothesis testing that we'll mention later always give the same kind of conclusions for these type of questions we see in part F. But to really get into hypothesis testing, we have to first talk about parameters again. So here's how the notes start in section 15.1. Chapter 15 is going to be broken down on a section by section basis very, very carefully. And for 15.1, all we're doing is saying what is a hypothesis and defining them. I don't want to go too far off this page since these are notes that you don't want to break in half across a day, even from Wednesday to Thursday. So we'll end on this right here, just indicating what a hypothesis is. Then when we come back on Thursday, we'll delve into it further, talking about the cautions, how to formulate hypotheses. And these problems down here are very similar to the homework problems as well in 15.1. But first, let's start at the beginning. At the beginning, we have to talk about what is a parameter. A parameter is anything that's describing your entire population, conflated with the sample, which is just referring to a subset of your population. So the parameter that we're interested in could be two things. The parameter could be mu, that's if our data is quantitative, or P. So if we have categorical data, exactly two outcomes, just like in chapter 13, we would use that parameter there. And that ought to go in the notes as well. Let's say for mu, just to emphasize because of its importance, that's for quantitative. It's kind of nice that this sort of answers why we fussed about quantitative data versus categorical data. It's because we were trying to get to this part of the notes eventually. Use P for categorical. Two outcomes. Which is kind of weird. We've done categorical data with 3, 4, 5 outcomes and so on. If you're curious how to do statistics with that, then our book actually just keeps on going. It's the chi-squared methods for 3 outcomes, 4 outcomes, and so on. But it doesn't look like we're going to make it that far. It wasn't even in the syllabus. So once we get a good handle on parameters, here's how a hypothesis test goes. A hypothesis test will use your sample data. It says to choose between 2 competing hypotheses. One is referred to as the null hypothesis. It's written as H0, but it's often read as H not. Not for zero, as our book describes. The alternative hypothesis we write as HA, or sometimes we might write it HA, is the competing claim. So we have two claims. The null hypothesis is a claim that's initially assumed to be true. Another way to say it is, your null hypothesis statement is the status quo. A statement that things are still the same, nothing's changed, that kind of statement. The alternative hypothesis is not the status quo, it's a big statement. Something has changed about the parameter, and our goal is to find evidence for HA being true. So as hypothesis testers, all of us as statisticians, we're trying to show the alternative hypothesis is the actual truth of the population. We begin by saying nothing's changed, then we look at the evidence in the sample data, and we use probabilities to assert the alternative hypothesis is true, or that we failed to show that it's true. But all that's really super abstract, like being really, really abstract. That's why hypothesis testing is tricky. We do it after confidence intervals. But here's a great way to get started. Here's our example. Let's define a parameter because hypothesis testing is all about parameters. Let's write out mu equals the average speed. Let's put here in miles per hour that Mike being me, drives to work in a 35 mile per hour speed zone. So that's our parameter mu. And now let's add just something extra to this to give it a little bit of conflict. Let's suppose Mike is summoned to traffic court, which could happen. It's never actually happened, but let's suppose it happened. And this is actually kind of special in a way, because if you watch like a lot of law shows, Law and Order, anything that deal with courtroom antics, the logic of what happens in a courtroom is exactly hypothesis testing, legitimate hypothesis testing. So what do you say always in the court of law? The defendant is assumed to be what? Innocent, right? That would be a statement that my speed was 35 miles per hour. So in the court of law, we first assume this. Here's the null hypothesis, H naught. It's a claim about a parameter, and we're trying to say I'm innocent here, so we'll put down colon mu equals 35 miles per hour. This is a statement that I never broke the law, that my average speed is the posted speed limit. That's the status quo, that no law was violated, and a court of law, you assume innocence right away. That's assuming the null hypothesis is true. Now, the statisticians are the prosecutors, essentially. The prosecutors want to show this is true. That's the alternative hypothesis, HA. And if they're trying to show the alternative hypothesis is true, and if they're trying to show that I am in fact really, really guilty, they would put here mu something 35 miles per hour. But what would you say ought to go here, right in the middle? Should it be less than or a greater than? Greater than, that would imply guilt majorly, right? That would mean I'm speeding and that I should pay for it, some kind of fee or something, maybe prison time, who knows? So that's what the alternative hypothesis would be. And we use probabilities called p-values to establish evidence for HA. So that's essentially what hypothesis testing is all about. In this silly example here with the court, it really goes that way. We assume the null hypothesis is true. We collect evidence as much as we can to show that, in fact, the truth of the null hypothesis is implausible in the face of the evidence, and then we say it must have been the case the alternative hypothesis was true. But here is the biggest and most confusing thing about hypothesis testing. If we can't show AJ is true, that I was actually speeding in that zone, this does not imply H naught is true. That's a really weird statement. In hypothesis testing, we're never trying to prove the innocence. We're just trying to see if we have enough evidence to say Mike is guilty as hell, he should be locked up. We can't find that evidence. It doesn't mean Mike is innocent at all. So in hypothesis testing, here's the big warning. We'll mention this again. We never conclude H naught is true. That's extremely easy to lose track of, so we'll mention that a lot as we go through the notes. But our purpose so far in these notes is just to think about hypothesis testing. When we come back on Thursday, we'll move through this document and potentially get into section 15.2 as well, moving a little bit further. But any last questions or comments then, folks, before we call it a night officially? Okay, I think this will be a great stopping point for us. We'll pick up next time, formulate our own hypotheses down here and just see how it goes, probably getting into section 15.2. But have a great day, folks. I'll see you all in Thursday's class.
What is all the final?
It looks like it's going to be up to chapter 15.
Is it everything?
It's going to be everything, but it's going to be, not every single thing will be on it, but a representative sample of all the problems.
And we'll look at your class, like your class time, or
It's going to be 5:30 to 7:30. Yeah, I believe it's on Monday, this classroom. Yeah. My other class has a final from 8 to 10 p.m. So I offered them to join this class if they felt really bad about it. You might see a couple strangers in here. That's going to be Monday on finals week. I'm not too sure the date either. I'm not terribly sure. Let me see. Finals week. Yeah, it looks like the 9th. Yes. That's a good thing to put in the calculator. Good call. Yeah, I just got the email confirmation of that, I think yesterday morning. So I need to update the Moodle website to put that all down here as well. Yep, have a good one.
that morning at 7.
7 a.m.
Yeah.
Ouch, sorry about that.
I'll figure it out. I don't know exactly what day it is. Anyway.
Don't hesitate to reach out to your professor because sometimes, I mean, I know I am, people are
I have
reasonable with
kids,
that,
and
yeah.
We're gonna take it out of the house before 8, because my husband works nights, so usually we tag team, but
Yeah,
it might be to where I'll just have him take the night off and we'll figure it out.
yeah.
Because once I'm done, I'll be done, and he's ready. He's like, when are you done for this?
Yeah,
I was like, then I'll have a whole month before I start again.
all over again, yeah.
Yep.
You know, it's a little bit easier in spring semester because you're kind of more familiar with how your schedule is going to be, the reality of it and all that
Yeah,
stuff.
well, I started last year, so
Oh, gotcha.
he kind of knows, but he's like so ready for this has been hard with football and all the sports and everything, so.
Yeah.
In spring, I still have sports, I have my girls softball stuff, so
Mhm.
hopefully we'll figure it out.
But you won't have to be worried about statistics. Yep, you
Nope.
betcha.
Nope, and I have to take college algebra, but I've
Oh, cool.
always loved algebra, so I've always been decent at math. I
Awesome.
wasn't worried, my sister's really struggled in statistics, but I've really enjoyed, like.
I'm glad to hear that.
This last test was
Awesome.
kind of hard, but I think it was just because of all the homework stuff that got messed up with the.
Yeah, that didn't help a
online.
lot. I agree.
I feel like if I could have got caught up before the test, it would have helped a lot more.
Yeah.
That was just me. So, but thank you.
Yep.
We'll see you.
See you later.
Have a good week. I guess we'll see you in a little bit.
Have a good rest of your week.